friends, welcome back to a new video. Today I'll be reading to you Forces and Motions Through Infographics. This is a new series. This is a science series. It's called Super Science Infographics. As most of you should know, infographics are sort of like posters, and they have information just in small little words. Let me read you the introduction. Learning about heavy physics concepts can sure weigh down your brain. You need to understand huge forces. Forces and motions through infographics. Rulers of the universe. Rulers of the universe. Do you have a future? Do you have a future in physics? Find out. Take this test. Do you wonder how basically everything moves? Do you like working with math and numbers? Is riding a roller coaster as a science experiment to you? How about gravity? Are you drawn to it? So, did you answer yes to any of those questions? Congratulations! You have what it takes to to be to be a budding physicist, a scientist who studies forces and motion. There is so much to there's there's so much to study too. There's so much to study too. Earth and Earth and everything in the universe is moving, and forces make that motion happen. They're the two rulers of the universe. Studying everything in the universe isn't easy. There is always more and more data about the way things move and the forces work. The new data means more questions. It can make your head spin. Physicists use graphs, charts, and other infographics to help sort through all the information. These graphics can make those big, mysterious ideas a bit clearer. Are you ready to join the fun? Let's get moving. Constant motion. You are always on the move, even if you're standing still. Earth is doing all the moving. It's in constant motion. It's hard to believe, isn't it? Let's take a closer look at motion. What is motion? Motion is when something moves. Here are two kinds of motion. It's hard to read. Translation. Translation is when an object moves on a line or a curve. Earth orbits the sun. It moves along a curved line around the sun. Rotation is another type of motion. It is when an object spins around its center of gravity. Earth does that too. It spins around its center axis. It takes energy to make motion happen. Potential energy is stored energy when it is used to make motion. It becomes kinetic energy. That energy that is being used. So that's translation, moving around, and that is rotation. That's translation, rotation, and as you take a look at the motion of a soccer ball, as you get ready, take a look at the motion of a soccer ball. As you get ready to kick the ball, you have potential energy. You launch it in the air, setting it into motion. It uses the kinetic energy to fly across the field in translation. The ball spins as it flies through the air. It's in rotation. So, as you can see these two pages. These are what you call infographics. They're small informations neatly setted, um, and they're making a big. It's just like a little bit of words, like not in those books where you see lots of them. And they're telling you something big in small words. So, and you can see this one, for example. I've made infographic about saving the Amber leopard, and it was simple, and maybe I might start sharing that with you all because read with me, learn with me the channel's name now. So anyways, let's see. Wheel of forces. You can't always see them, but you can see what they do. Sound mysterious, don't they? Their forces, different different types of pushes or pulls. Different forces affect motion in different ways. Sometimes sometimes the force is you. Sometimes the force is acting upon you. And many times more than one force is applied at the same time. Spin the wheel to check out some of the different forces at work in the universe. Um, the reason they're telling you that spin the wheel because this is on online, but when it's actually in book form, you can actually spin the wheel. But balanced and unbalanced forces. Forces are balanced or unbalanced. When they're balanced, they're equal. When they're unbalanced, they're unequal. A sled can show you both balanced and unbalanced forces. At the top of a hill, gravity pulls down on the sled, and the ground pushes up in equal forces. When the sled moves, friction pulls the sled down the hill. So you can see in this picture, the person's pushing down on it, the ground's pushing up, and just falls down. It's hard to read. Oh, this is what we read, right? Um. So we can. I'll just try my best to read this. Electrical. This force is the push or pull of an electric charges. It is made by atoms that repel when pushed too close together, and when they attract when pulled apart. Magnetic. This force can be a push or a pull. It is a force made between magnets and magnetic materials such as iron. Gravity. This force is a pull. It all objects with mass create this force. This transition. This force is a pull. It happens when things are pulled tightly, such as string or rope. Spring. This force is a push. It happens when a spring has been pushed down or stretched out. The force occurs when the spring returns to its normal. Um, this force is a push. It supports objects that touch it. A table pushes a table pushes up on a book lying on the table with normal force. Friction. This force is a push. It happens when two things rub together. Friction can make moving something difficult, but friction is helpful too. Friction allows us to stand up and walk. Without it, we'd slip and slide everywhere. Have I read electrical? So electrical. The force is the push or pull of electricity charges. It is made by atoms that repel when pushed too close together, and, and when they attract and when they attract when pulled apart. Did you happen to notice that forces require two objects for what? For interact? They do. So this is our third infographic. This is actually quite nice. Nothing, but I think it has a bunch of information. But still, I really like how they added that Earth. And on every new page, I will comment on it. So please don't mind. Kings of gravity. We all feel the effects of gravity, but gravity wasn't understood until Isaac Newton and Newton and Albert Einstein came along. Newton first thought about how gravity acted, and Einstein built upon that knowledge, figuring out what caused gravity. And take a look at how these two brilliant scientists changed the way we think about gravity. So, Isaac Newton. Isaac Newton 1642 to 1727 was an English physicist and mathematician. Uh,
Mathematician.
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 And mathematician. He realized that gravity holding objects to Earth's surface extended far above Earth. He believed that the same gravity held the moon in Earth's orbit. He called this law of universal gravitation. This theory looked at how gravity worked through space or distance. Newton's idea described the strength of gravity very well. He knew it existed and was strong enough to hold planets in orbit around the sun. His theory had a problem though. He couldn't explain how gravity worked. Newton showed that gravity is the force that kept the moon. Newton showed that gravity is the force that kept the moon in Earth's orbit. Albert Einstein. More than 200 years later, Albert Einstein, 1879 to 1955, started thinking about light. He found that the speed of light was so fast that nothing else could go faster than it, not even gravity. He started thinking about how gravity worked with space and time combined, space-time. Einstein discovered that a large mass curves space-time. It explained how gravity worked. For example, planets move around the sun in a circle. This is because the planets follow the curve in space-time that is made by the sun. This was Einstein's general theory of relativity. Einstein showed how a planet bends. A space-time how planet Einstein showed how a planet bends space-time, keeping an object in its orbit. So this is the not sure which one. I think it's the fourth. I think it has way too much information. Still quite nice. Red, yellow, blue, not a bad combination. I quite like this one. And I see they used the same person from here onto there because it's probably one person who did all the illustrations and stuff. Ollie and anatomy. Skateboarding tricks are all about physics. Forces rule how fast a skater can go. They also rule how much air a skater can get. The ollie is a basic skateboarding trick. It's one that every good skater needs to master before trying harder tricks. Check out the physics involved with the ollie. Before the trick starts, forces are already in action. The weight of the skater pushes down on the board. Earth's gravity pulls down on the board and pushes the ground also pushes up on the board. The skater crouches down on the board. A low center of mass will help him get more air on the jump. The skater pushes the board forward. It moves faster and faster. Now it's time for the trick. The skater straightens his leg and raises his arms. This makes the skater's rear foot push down on the tail of the board. The rear The rear foot has more force pushing down than the front foot. The nose of the board lifts up. The tail hits the ground. The ground pushes with upward force on the tail. This makes the board bounce up. The In the air, the skater drags his front foot forward. It stretches against the rough surface. This causes friction. Number 5. The skater starts pushing his front foot down on the nose. He pulls his rear foot up at the same time. The rear wheels go up and the board straightens out. Number 6. The board and the skater use gravity to fall back to the ground. Okay, number 7, the last thing. The board hits the ground. The force of the ground pushes back on the board. The skater bends his leg. It helps the force spread out in his body. His legs might be hurt if he does not do this. Laws of motion. Remember Isaac Newton? He thought about motion too, not just gravity. He developed 3 laws of motion. The laws are about how objects interact. The objects can be great or small, from massive planets to tiny atoms. They apply to people too, including you. These are 3 laws of motion. Number 1. An object at rest or in motion stays that way until acted on by a force. An object will not accelerate until the accelerate to bring about earlier to move or cause. An, an object will not accelerate until a force acts upon it. An object stays at rest or moving at the same speed in the same direction until acted upon by a force. Force equals to mass times acceleration. The more force on an object, the greater the more force the more force put on an object, the greater the acceleration. Also, the same force put on objects of different mass causes different amounts of acceleration. Number 3, for every action there is an equal and opposite reaction. fast, faster, and fastest. It's fun to go really fast. Ever tried on your bike? Speed? Ever ever try it on your bike? Speed is how fast something is moving. To find speed, you need to know how long it took something to get from one point to another, and you need to know the distance that was traveled. There's an equation for determining speed. It is speed equal to distance slash time. Check out these amazingly fast speedsters. Fastest human, U- Usain Bolt, 28 M MP4H miles per hour and 45 sorry kilometers per hour. Fastest land animal, cheetah, 64 miles per hour and 103 kilometers per hour. Yeah. Fastest car, 20, 267 mile per hour and 430 kilometers per hour. Fastest train, 302 miles per hour and 486 kilometers per hour. Sound, 741 miles per hour and 1193 kilometers per hour. Earth's orbit, 60, 67,062 miles per hour, 107 uh, 107,952 kilometers per hour. Light, 600 670 million 615,200 miles per hour, and then 1,079,250,584 kilometers per hour. This is quite nice. There's like a roller coaster, a gray ground, and very small information. That's good. Roller coaster thrills. Twists, turns, upside down rolls, and terrifying plunges. They're all part of a thrilling roller coaster ride. But how come riders don't fall out of the cars? And why do the cars stay on tracks? It's because forces, energy, and interior are at work. Roller coasters don't have engines. A cable or a lift pulls the cars to the top of, of the first hill. The cars gather lots of potential energy on the way up. The higher the hill is, the more energy that is stored, and if the cars have more energy, they will move really fast on the track. Now it's time for kinetic energy to take over. Gravity pulls the cars pulls the cars, they speed down the hill. Friction from the car's wheels help keep the cars on the track. The cars gather enough energy and the, to make it to the top of the next hill. And Newton's first law kicks in too. Inertia keeps the cars moving up the hill. And the cars speed up into the loop. Gravity pulls towards the center of the loop. When the cars are upside down, the normal force of the track also pushes on the cars. Together these two forces cause the cars to go on a circular path instead of a straight line. The cars lose energy toward the end of the track. Towards the end of the track. Wind and friction on the track slows down the ride. The cars can only get up smaller hills now. The brakes at the end of the car stop. The car the brakes at the end of the ride stop the cars. Time to get out. And this is pretty nice. Uh, this is a pretty nice one. I like it. Cool. Nice color choices. And the reason I'm talking about why these things look it's because I'm thinking about doing one together. I'm gonna make an infographic with you guys. It could be about anything. Powerful magnets. You can find magnets in just about every machine. They're hidden inside most of the things we use every day. But not all magnets are the same. Some are extremely powerful and some are very weak. Take a look at some of these strengths of different magnets. Amazingly, what is this? Maglev trains. Some trains don't even have engines. Instead, strong magnets and electrical current power them. The trains glide on air. It makes for a smooth and incredibly fast 400 kilometers per hour. They're quieter than regular trains and better for the environment too. Here's how magnets and electric current make these work. So this is a train. That's the rail. Guide magnet, current in track, train magnet. Guide magnets control
Propulsion.
propulsion. Yes. Magnetic strength is measured in Telsa or Gauss. 1 Telsa equal to 10,000 Gauss. What does that say? 45 Telsa hybrid strong. The 45 Telsa hybrid, strongest research magnet in the National High Magnet Field Laboratory. Junkyard magnet that can shift a car. Miri scanner. Average fridge magnet. Earth's magnetic field. I like that. And this is, I read it. Yeah, okay. And this is the biggest magnet. You can see this red big circle, then this small, and then this, and this. These are all different kind of magnets. This huge red one is the best one. The 45 Tulsa hybrid. Strongest research magnet at the National High Magnet Field Laboratory. This is the strongest. This is a junkyard magnet. It can lift a car. It's a Muri scanner magnet. This is a fridge magnet, the one you use at home. And Earth's magnetic field. Move forward. This one's quite nice. It's like a racetrack. Surviving a NASCAR crash. If you drive fast, you can crash hard, and NASCAR cars reach some of the highest speeds possible. Car crashes are part of the sport, and crashes are also examples of Newton's law of motion in action. Here's how specially designed NASCAR cars and other safety devices keep the driver safe during crashes. 1. Kinetic energy and speed have a lot to do with each other. The faster the car goes, the more kinetic energy it has. A crash stops the forward motion of the car, but there's a lot of kinetic energy in the car. It has to be released. It becomes heat and sound and is transferred to different parts of the car. The energy has to go somewhere. A NASCAR car is designed to control where the energy goes. It has crumple zones at the front and the rear of the car. During a crash, the front and the rear crumple first. Around the driver, the car frame is stronger. Isaac Newton found that an object in motion stays in motion unless a force acts upon it. When speed is added, the object has momentum. So while the car crushes around the driver from the force of the crash, the driver has still a forward motion. That is why seat belts are so important. Without seat belts, the driver would just fly forward and be severely injured. A NASCAR seat belt has 6 straps that meet near the driver's pelvis. A special a special device also supports the driver's head. The systems provide the force that that stops the driver's momentum. The car is totaled, but the driver walks away with little to no harm. The car's design and the driver's safety devices worked perfectly. Both used physics to protect the driver. So, way too much information, I think. 10 jobs for simple machines. Do you ever think it's that too hard? Think that's too hard. I wish I could make it easier. A simple machine may just be the thing you need. Simple machines are the basic tools that make work easier. There are lots of tools that you can use every day. Check some of the cool jobs that are made with easier machines. The 6 simple machines. These 6 simple machines are used in millions of ways. Inclined plane, wedge, screw, lever, pulley, wheel, and axle. Chop some fi- oh, no. Get from English class on the first on the second floor, the first floor gym in less than Get from English class on the second floor to the first floor gym less than in less than 2 minutes. Stairs are a kind of inclined plane. 2. Chop some firewood for a chilly winter day. A wedge on and the axe splits the wood. Verse 3. Raise the flag Raise the flag high on the 4th of July. A pulley makes this work easy. Keep the strawberry jelly in. Keep the strawberry jelly in and the ants out. Jar lids you can use a screw system to stay on. Get a cool drink of water next time you're in the country. A pulley in a well makes it easy to bring a, up a bucket. Cut yourself a big slice of pepperoni pizza. A rolling pizza cutter is a sharp wheel and axle. Shed some light on the night. Put a new light bulb in a lamp. A screw keeps it in place. No more excuses. Keep your homework from flying away in the wind. Staple it together. A stapler is a kind of lever. Move your enormous fossil collection. In an inclined plane is a great way to move heavy things. They can go from low points to high points with ease. Is there anything? There's 10. Cruise through the city on your lowrider bike. It uses a wheel and axle to work. Twinkle, twinkle, little satellite. Turn on the television or make a call on a cell phone. You're instantly accessing information sent by a satellite. The sky is full of these complex machines. Satellites use two or more simple machines. That's what makes them complex. More than 1,000 satellites orbit the Earth. The United States has the most satellites, more than 400 of them. Here's a close-up view. Here's a close-up view of these complex machines. A sky full of satellites. The United States owns many of the satellites in space. Here's what they're used for. Commercial, 200. Government, 116. So commercial, 200, 44%. Government, 116, 26%. Military, 128, 28%. And civil, 11, 2%. Levers adjust the antenna. Screws hold the different parts of the satellite together. A satellite orbits the Earth in space. It receives information from machines on Earth. Machines on Earth receive information from the satellite. Interesting infographic. Rocket power. Breaking away from Earth's gravity isn't easy. Rocket scientists know all about that. That is one of their biggest challenges when designing rockets meant to go in space. Guess where they began? With Isaac Newton and his equations about gravity, force, mass, and
Acceleration.
acceleration. Here's how rocket design makes use of Newton's idea. Gravity force near Earth's surface pulls down on the rocket. A rocket must move a faster rate than gravity. If it doesn't, it will make high enough it will not make it high enough to escape gravity's pull. The higher the rocket gets, the weaker gravity's pull is. Newton's equation for is force equals to mass times acceleration. Newton said that a force had to be put upon a mass to make it accelerate. Newton also said that every force has an equal and opposite force. For rockets, this means that the force of the gas shot down from a rocket equals the force pushing it forward. Scientists measure that the amount of gas at what speed is pushed out. From this and the mass of the rocket, they can figure out what speed the rocket will move forward. Chemical reactions in the fuel tanks create gases moving at very high speeds. The gases are released from the tail. This makes the opposing force and the rocket shoot forward. As the fuel in one tank is spent, it falls off the rocket. This makes the rocket lighter. It uses less and less fuel the higher it gets. Okay. Buoyant submarines. It doesn't mean a whole lot of sense. Very heavy ships and submarines should sink in the ocean, shouldn't they? But they don't. That's because of buoyancy and density. When an object is in water, some water is displaced. The weight of that water is the buoyant force on the object. The density of an object is its mass divided by its volume. For an object less dense than water, the buoyant force can be larger than the object's weight. This lifts it partly out of water. But an object more dense than water will sink. Its buoyant force is less than object weight if the object has some density as water. It equals the buoyant force. It neither rises or sinks. Submarines need to be able to control their buoyancy. Here's how they do it. Vents, outer hull and inner hull. Ballast tanks and opening. The submarine rises underwater. Its ballast tanks are filled with air. The submarine has less density than the water. It is pushed up to the water surface. The buoyant force is greater than gravity's force. The submarine floats under the water surface. Its ballast tanks are filled with water. Air is forced out of the tanks. The submarine has around the same density as the water. It does not sink, and it is not forced to the surface. The buoyant force is equal to gravity's force. So, that is the end of the book. There is a whole other series. There are one, two, three, four, five, plus counting this is six, and we have five more books to read. I want to check out the age level for you guys. So the age level for this is 8 to 11. So kids from 8 to 11 can read this book, and maybe even older people, but maybe like people younger than 8 might not get this book. So share it with your friends and family and tell them to subscribe. And if you like this book, please like, share, and subscribe. And please hit the bell button for if you want to see more videos. And I'll see you next time. Goodbye.